Welcome back on my channel. Uh, we will continue class 12th and chapter 9 ray optics and optical instruments. 12th class. Okay, the introduction is sorry. Nature has endowed the human eye retina with the sensitivity to detect electromagnetic waves with a small range of electromagnetic spectrum. Electromagnetic radiation belongs to the region of the spectrum wavelength of about 400 nanometer to 750 nanometer is called light. It is mainly through light and the sense of the vision that we know and interpret the world around us. There are two things that we are intuitive mention intuitively mention about that about light from common experience. First, that is travel with the enormous speed, and second, that it travel in a straight line. It look some time of the people to realize that the speed of light is finite and measurable. It presently accepted value in vacuum is c equal to 2.9979248 into 10 to the power 8 in meter per second. For many purposes, it suffices to take c is equal to 3 into 10 to the power 8 meter per second. The speed of light in vacuum is the highest speed attainable in nature. The intuitive notion that light travels in a straight line seems to contradict what we have learned in chapter 8, that light is an electromagnetic wave of wavelength belonging to the visible part of the spectrum. How do we reconcile the two facts? The answer is that wavelength of the light is very small compared to the size of the ordinary object that we encounter commonly, generally the order of a few centimeter or larger. In this situation, as you will learn in chapter 10, a light wave can be considered to travel from one point to another along a straight line joining them. Path is called ray of light, and bundle of such rays constitute a beam of light. In this chapter, we consider the phenomena of the refraction and dispersion of light using the ray picture of the light. Using the basic laws of the reflection and refraction, we shall study the image formation by the plane and spherical reflection and reflection surface. We then go on to describe the construction and working of some important optical instrument, including the human eye. Okay, the first one is reflection of light by a spherical mirror. Okay, this is the figure in which we will continue. We are familiar with the laws of the reflection, the angle of reflection. Okay, that the angle between the reflected ray and the normal to the reflecting surface or the mirror equal to the angle of the incidence angle between the incident ray and the normal. Okay, this is the incident ray and this is the normal and this is the reflected ray. Okay, and this is the mirror. Okay, the next one is also that the incident ray, reflected ray and the normal to the reflecting surface at the point of the incidence lie in the same plane. These laws are valid at each point on any reflecting surface, whether plane of curve. However, we shall restrict our discussion to the special case of the curved surfaces, that is spherical surface. The normal in this case is to be taken as normal to the tangent to surface at the point of incidence. That is, the normal is along the radius, the line joining the center of the curvature of the mirror to the point of the incidence. Okay, we have already studied the geometric center of the spherical mirror. Is it is called a pole, while that of the spherical lens is called the optical center. The line joining the pole and the center of the curvature of the spherical mirror is known as the principal axis. In this case of the spherical lenses, the principal axis is the line joining the optical center with its principal focus, as you will learn. See later. And we can see this is the upward positive height, and this is the incident light, and downward height, downward negative distance against the incident light negative. Okay, x-axis, and this is the distance along the incident light positive. Okay, now sign convention. To derive the relative formula for the reflection by the spherical mirrors and reflection by the spherical mirror lenses, we must first adopt a sign convention for measuring distances. In this book, we shall follow the Cartesian sign convention. According to this convention, all the distances are measured from the pole of the mirror or the optical center of the lens. The distances measured in same direction as the incident light are taken as positive, and those measured in the direction of the opposite to the direction of the are incident light are taken as negative. The highest measure upward with respect to x-axis and normal to the principal x-axis or of the mirror. Lens are taken as positive. With the common accept convention, it turned that a single formula for the spherical mirror and a single formula for the spherical lenses can handle all different cases. The next one is focal length of the spherical mirror, and we can see this is the figure. Okay, so we will continue the figures. When a parallel beam of light is incident on a concave mirror, okay, this is the concave mirror and this is the convex mirror. Okay, the rays are paraxial, that they are incident at point close to the pole P of the mirror and make small angles with the principal axis. The reflected ray converge at a point F on the principal axis of the concave mirror. Okay, for a convex mirror, the reflected ray appear to diverge from a point to point of point F on its principal axis. Okay, in B, the point F is called the principal focus of the mirror. If the parallel paraxial beam of light were incident, making some angle with the principal axis, the reflected ray would converge from a point to a point in a plane through F normal to the principal axis. This is called the focal plane of the mirror. Yeah, we can see the focal plane of the mirror. Okay. The next one is the distance between focus and the pole of the mirror is called the focal length of the mirror, denoted by F, and we saw the F is equal to R upon 2. Okay, where R is the radius of the curvature of the mirror, and the geometry of the reflection of incident ray is shown in figure 9.4. You will see in the next page. Okay, the next one is, let C be the center of the curvature of the mirror. Consider a ray parallel to the principal axis striking the mirror at M. Then the CM will be perpendicular to the mirror M at M. Let theta be the angle of the incidence and MD. Okay, this is the MD. Okay, this is theta and this is theta, because I is equal to R, and this is also theta, and this will become 2 theta. Be the perpendicular M on the principal axis M. Then angle MCP is equal to theta and angle MPF is equal to 2 theta. Okay, tan theta is equal to MD upon CD, and tan 2 theta is equal to MD upon FD. This is the equation 1. Now for a small theta, which is true for paraxial rays, tan theta 2 theta and tan 2 theta is 2 theta. Therefore MD upon FD equal to 2 MD upon CD. So we can say FD is equal to CD upon 2. Now for a small theta, the point D is very close to the point P. Therefore FD is equal to F and CD is equal to R. And in equation 9.2, F is equal to R upon F. 2. Sorry, 2. F is equal to R upon 2. The next one is the mirror equation, and this is the figure in which we will describe. The ray emanating from a point actually meet at another point after reflection or refraction. That point is called the image of the first point. The image is real if the ray actually covers to the point. It is virtual if the ray do not actually meet but appear to diverge from the point when produced backwards. An image is thus a point-to-point corresponds with the object established through reflection or refraction. Okay. In principle, we can take any two rays emanating from point on an object, trace their paths, find the point of the transections, and thus obtain the image of the point due to the reflection at a spherical mirror. In practice, however, it is convenient to choose any two of the following rays: the ray from the point which is parallel to the principal axis. The reflected ray goes through the focus of the mirror. Okay. The ray passing through the mirror, the center of the curvature on a concave mirror, or appearing to pass through it for a convex mirror. The reflected ray simply retraces the path. Okay, the third point is the ray passing through the directed outwards. The focus of the concave mirror are appearing to pass through directed onwards. The focus of a convex mirror. The reflected ray is parallel to the principal axis. The ray incident at any angle at the pole. The reflected ray follows laws of reflection. Okay. Now 9.5 figure. This is the figure in which we are talking. The rays diagram considering the three rays. It shows the image A dash B dash in case of the real of an object AB formed by the concave mirror. It does not mean that only there three rays emanate from the point. An infinite number of the rays emanate from any surface in all directions. Is it? Thus, point A dash, the image of the point A, if every ray emanating at point A and falling on concave mirror after a reflection passes through the point A dash, we know derive the mirror equation on the relation between the object distance u and image distance v and the focal length f. Now in two right angle triangle a dash b dash f dash f and angle mpf similar for paraxial ray mpa can be considered to be the straight line perpendicular to cp. Therefore a dash b dash a dash upon pm equal to b dash f upon fp. So we can write b dash a dash upon ba equal to f dash b upon fpa, since pm is equal to ab. Okay, since angle apb equal to angle a dash pb dash, the right angle triangles a dash b dash p and abp are so similar. Therefore a dash b dash upon ba equal to b dash p upon bp. Comparing b dash f upon f dash p, b dash p minus f p upon f p equal to b dash p upon bp. Equation. Okay, 9.6. This is the equation. Is a relation involving magnitude of distances. We now apply the sign conventions. We note that the light travels from the object. The light travels from the object to mirror mn mpn. Then this is taken as the positive direction to reach, to travel opposite to the direction of the incident light. Hence all the three will have the negative sign. Thus b dash p is equal to minus b and f p is equal to minus f and bp is equal to minus u. Using these equations in 9.6 in this one, minus b plus f upon minus f is equal to minus b upon minus u, ये कैंसिल हो जाएगा. Minus b minus b minus f upon f equal to b upon u. So when we will do it, so divide, then it will become b upon f plus 1 minus 1 and equal to v by u. On dividing by both side b, we will see 1 upon b is equal to 1 upon e plus 1 upon f. This is the mirror equation. Okay. The size of the image relative to the size of the object is another important quantity to consider. We define linear magnifications m as the ratio of the height of the image h dash to the height of the object h. M is equal to h dash upon h. H and h dash will be taken positive or negative accordance with the accepted sign convention, and in triangle a dash b dash p and abp here. B dash a dash upon b equal to b dash p upon bp. With the sign convention, it becomes h dash upon h is equal to minus b upon u. That's we can say that b is equal to minus h dash upon h is equal to minus b by u. Okay, so here we derive the mirror equation 9.7 and the magnification formula. In case of real inverted image formed by a concave mirror with the proper use of the sign convention, these are in fact valid for all these cases of the reflection by a spherical mirror, concave or convex. Whether the image formed is real or virtual, 9.6 shows that the red diagram is virtual and formed by the concave mirror and convex mirror. Okay, we can see this is the concave mirror, this is the convex mirror. Yeah, written here. So we have to next topic we will continue in the next video. Thank you for watching.